I'm going to be creating this video segment for the problem that you see here. It's an assembly made of 3 pins and a disc, and then the top 2 pins at the end faces are clamped or fixed, and then the bottom pin or the middle pin is actually pushed in some direction by a given amount. So I will go ahead and create the assembly, and this was a final exam problem from a few years back. So insert insert a disc, insert a new part in there, and I'm going to call this thing the disc. That's the disc with 3 holes. So disc and the disc. Okay. And let's make it. We go to part design by double clicking on this on a convenient plane. On that vertical plane, I will draw a circle, and I'm going to make this radius 6. I think the radius of this diameter was 12. The radius is 6. Okay. And then we draw 3 circles here. This is the one in the center. The radius of all of these is 1. And another circle over there. And another one down here. We're going to position them in just a minute. Okay. And then this one is diameter 2. This one also, not that one. This one is also diameter 2. And so is this one. And let's put some dimension between the center of this and that line. That's going to be 6. Oh, I made a mistake. This diameter, this one should have been 24 actually. That should have been 24. Diameter is 24, radius is 12. Okay. Yeah, good, good. And then another one between the center of this circle and that guy is also 6. Okay, so this is supposedly that disc that you see there with 3 holes. So exit, pad it. The thickness you're told that it is 2 inches. So we make a mirror extent 1 inch in each direction, and that gives us what you want. Now I can insert the pin, insert a new pin, a new part in there, and I'll call it the top pin. Right click, properties, top pin, and top pin. Top pin. Okay, let's make it. So top pin, I'm going to project on that let's see now, YZ plane. I will project, sketch, and project that circle. There we are. Exit, and then pad it symmetrically by 3 inches in each direction, so total of 6 inches. So that's 3 inches in each direction, and that's the top pin. Okay, now go back here, insert, new part. So no, of course you can use that pin by copying it, but I'd rather make it properties. I'm going to do the middle one, middle pin. But middle pin, and down here also middle pin. Okay, and make it. So go there on that same YZ plane. I will sketch. Repeat this process 3 times. This is ridiculous, but that's okay. Exit, pad it in each direction 3 inches, and finally go up there, insert, new part, say no, and this is going to be the bottom pin. Right click, properties, bottom pin, And same thing down here, bottom pin. Okay, let's make it. So go in there on that YZ plane, sketch, project that circle, exit, path it in both directions, 3 inches in each direction. So that's 6. Okay, let's go ahead and save this thing. By the way, this entire thing is made out of steel, so we go to assembly level. So apply material. Where is this? Apply material. Metal out of steel on the entire assembly. And okay. Now we're going to save this. File, save management, save as, desktop, new folder, assembly problem 2, or assembly problem, assembly disk and pin. Disk, pin. Okay. And we say open and say OK, save and OK. Alright, now here's the situation. We are told that this top pin, the 2 ends are fixed, clamped, and the same thing with the bottom. And then we are taking the face here and the face on that side and pushing it in a certain direction, direction being direction Y here, by some amount. Okay? So we obviously have a plane of symmetry, and that plane of symmetry is the XY plane and the YZ plane. Both YZ plane and the XY plane. See that? The amount of displacement is 0.004. Okay, so we have 2 planes of symmetry. XY, cutting it with the XY plane, and cutting it with the YZ plane. Now we can do these simultaneously in the assembly while we're here. Click on the split, select the plane. It says these 4 parts are affected. Do you want all of them? The answer is yes. Which side do you want to keep? Okay, we keep that side. So this is the way it went. And then we also have to cut it with the XY plane. Okay, so again the saw, split, this plane. It says these are all affected. Are you sure? The answer is yes. And if it doesn't work, of course you're going to fix it. So there we are. This is it. The top and the bottom behave exactly the same way. Alright, so let's save everything. Okay, we go to generative structure analysis. Catia immediately measures these 3 parts. Now, of course, the disk itself is going to have a lot bigger element because of its size, and I'm going to change that. So notice that this one is for the disk. I'm going to change this thing to be maybe 0.3 or 0.2. We'll see how it works. Yeah, and then the top pin, I'll make it 0.2 so that you can see it better. And the bottom one also well, actually let me make it 0.25. How about that? Because I can't see it. Well, here 0.25, and this one 0.25. 0.25. Okay, very good. So let's look at the mesh now. Right-click Mesh Visualization. There we are. Okay. If you want different colors here, so let's go to Properties, Graphics. For example, for the pin, I'm going to make it yellow. And also for the other pin, I'm also going to make it yellow. Properties, where the disk itself is kept at blue. All right. I think these are too small, but our problems are simple, so we just leave it like this. Okay, fine. Now deactivate that, and let's start putting our restraints. So this end is clamped. Okay, let's put our surface sliders here, planes of symmetry. This is a plane of symmetry, that is a plane of symmetry, and that is a plane of symmetry. And incidentally, this is a plane of symmetry, so is this, and so is that. So we took care of all planes of symmetry, no problem. Okay, and now we want to take this pin and push it in the y direction by 0.004 according to what the problem says. So we do a user define on that face, and in the direction y, see that? First you make it 0. Oops. First you make it 0, and that's what this thing does, and then you can change it. So enforce displacement on that restraint in the direction y, so 0.004. I think that's what the problem says. Okay, now before we run the problem, we have to create connections between these. So we create, these are contact connections. We discussed about them in the class. So for the first component, the surface of this pin. For the second component, I'm going to hide this pin and select the surface of the hole. And this is going to be contact. And I do another connection, surface of this pin. And for the second component, hide this and select the surface of the hole. Also contact. Now what we have here, we have the contact. Let's go ahead and do that. So where is the contact connection? Right there. It's in the face-to-face connection properties toolbar. So this is contact. And once again, this is contact. Don't fool around with clearance and friction and things like that, please. So let's bring these pins into the show mode. Although that's not necessary, we can go ahead and run the problem. Okay, and save the analysis, file, save management, save the analysis in the same folder, which was assembly of disk and pin, yep. Okay, and run it. Ignore the warning. And that's it. So let us look at our deformation and animate it. If you want to see a bigger, exaggerated more so that you can see it better. So let us not use 252, the default. Let me use 400. There. Maybe more. 800. Okay. Actually, let me clear all these things that we don't want. Hide this. Hide the mesh. Oh, not this, not the mesh. Hide these things. Hide. 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 Let's hide all the restraints, all the properties. Let's hide the restraints and the load. Okay. Now here's what we did. This actually, it was too much of an exaggeration, so let's put it back to 400. Okay, good. And we can animate it. You see that it works fine. In other words, the top pin was clamped. This bottom one is pushed in a certain direction Y, by the amount given. If you look at the displacement, change it to average ISO, change the rendering to material shading. You can see that. And if you want to look at the stress, one MESA stress, obviously the biggest stress is going to be in this area, both maybe due to bending, maybe due to the fact that this is pushing on that. Now, I think in the question you're being asked how much force is needed to cause this displacement. So what you do is, first of all, deactivate this plot. All right. Okay. Let me change the rendering here. I don't like this material shading rate rendering. Okay. So right click, resultant sensor, reaction sensor, and then select the restraint that you put in pushing this. So right here, I think this was that guy, okay? And then update result. So you get roughly almost 4,000 pounds. Now remember, you have to get the actual force that is needed for creating deformation, because this is for half of the model. If you want to get the actual one, you need double of that on this side, 4,000 on this side, and 4,000 on the other side, okay? 4,000 on this side and 4,000 on the other side. That's a lot of force, but remember, this is a piece of steel and 2 inches thick, so it doesn't surprise you that there's such a... So the answer to this problem is actually this thing times 4, not times 2, times 4, because you have to, there's the top and the bottom, that means you double this, but there's the other side, which is another double, so that's 4. So that's pretty much it.